We're going to talk now about properties, particularly acidity of the hydrogens in carboxylic acids. So we're going to be remembering a qualitative tool that we use without knowing pK chart, and that tool is ARIO. So and we're going to be analyzing where the charge is, what type of atom in the conjugate base of these acids, and then whether we have or not resonance effects, then that is the art, then inductive effects in the I. But I'm going to first go to, say, the A, the atom type, and resonance effects. A little note here about what is a carboxylic acid. Remember that in a carboxylic acid, you must have this carbonyl in next to it, the OH. This molecule right here is not a carboxylic acid. It does have an OH, and but this group is a ketone, and that's an alcoholic group. And in fact, if we are naming that, so 1, 2, 3, and 4, that's 2-butanone, but is 4-hydroxy. 2-butanone, and that is acetic acid. Okay, different. Pay attention to that. Also, this is also a carboxylic acid, so we have the functional group, but this is an aromatic carboxylic acid. That is benzoic acid. This is not a carboxylic acid. This is a phenol. We have the OH directly attached to the aromatic ring, so phenol. And lastly, this is not a phenol, it is an alcohol. This is cyclohexyl, cyclohexanol, to say better. Cyclohexanol. All right, phenol, and this is my parent chain. So now, having said that, let's analyze the conjugate basis of this. Why? What is the properties, the acidity like for carboxylic acid relative to phenols and even alcohols. So I'm going to draw the conjugate base of acetic acid. That conjugate base is acetate. I think this is coming very light, so I'm going to redo that in another color. Just not all the colors show as bright. Let's try the blue. That works better. Okay, so this is a conjugate base of acetic acid, so acetate. Now I'm going to draw the conjugate base of phenol. So I'm going to grab a carboxylic acid, a phenol, and an alcohol for my example about acidity. So the conjugate base, you remove that one proton, and here you will have phenolate. Lastly, in the alcohol, if you remove that proton, the acidic proton, you will get an alkoxide. That's that. Analyzing ARIO, if you analyze the conjugate bases, all have the negative charge on an oxygen. So oxygen in all of them, so it's the same. I cannot tell whether they are different or not as acid strength. So we're going to go to the next effect. So here in the cyclohexanol, in the alkoxide, we don't have resonance effects because this carbon right here is sp3 hybridized sp3. So these electrons are localized, so no resonance. So I cannot stabilize that negative charge by doing electron delocalization. However, in the phenolate, I can. The lone pair here is allylic, so I can delocalize those toward the ring. And I'm going to draw the resonance structures that result from that. So this is now O double bond, and I'm going to have a negative charge here. And then I can continue to resonance because, again, the pair of electrons here is at an allylic position, so I'm going to keep moving them. And the next resonance structure will have, again, double bond here, but I'm going to have double bond and the electrons are here. So negative charge here. And again, allylic position, so I can move those over here. And I will have double bond, and that doesn't show well like a double bond. Let me redraw it. It came out too close. Okay. Double bond here with the oxygen. So now I have a resonance structure. So it is resonance stabilized. And I can put that negative charge these three carbons. So besides the oxygen. So phenol, because the phenolate DNI and the conjugate base can stabilize that negative charge, is more stable conjugate base, therefore weaker base. So phenol is more acidic. The more stable the conjugate base is, the more acidic the compound initially we were analyzing. So phenol is more acidic than the alcohol. Now let's analyze the, say, phenol versus a carboxylic acid. When we have a carboxylic acid, we can also have resonance. So again, in all of them, the atom was the same, is oxygen, but here you have an allylic lone pair. So you can do resonance here. And what is interesting of this resonance structure is now, and the resonance structure is identical to the previous thing. You're going to have charge on oxygen. So in this case, carboxylic acid, this resonance structure, these two contribute the same to the hybrid and contribute, say, to the same extent. The charge is evenly distributed between the two oxygens. So it does much better to have the negative charge on oxygen than having on a carbon right here. So despite that here we have more than greater number of resonance structure, these structures contribute more to the hybrid. So in fact, that charge in the carboxylate, the hybrid looks like that. Delta negative, and that is explaining that that charge is, again, delocalized between the two oxygen. So this base is more stable, the conjugate base. So weaker base, stronger acid. So what is my ranking? Because of resonance, carboxylic acids are more, this is two carboxylic acid, but I'm going to explain why I do this sign here. But carboxylic acid are stronger acids than two carboxylic acids. Than phenol and phenol are more stronger acids. So this is acid strength. And why do I have here the, well, actually, that's not right. I'm going to remove that. I thought about it. But, no, it's not. But we're going to see why. What is the difference between benzoic acid and acetic acid that I have here? Let's see. One case we have a metal. In the other case, we have a phenyl group. So, okay, but what it does. So when we have a phenyl group, this is, say, considered an electron withdrawing group. And now we go to inductive effects. So when you have electron withdrawing groups, let me continue to erase this because I'm going to need more room. So this is the ranking for now. But between these two carboxylic acids, let's say, talking about another effect. Here I have a metal, here I have a phenyl group. So phenyl groups are electron withdrawing. So we're going to say electron withdrawing groups. Right here. The electron withdrawing group, so phenyl versus metal, help stabilize the negative charge of the conjugate base. So in other words, because it's withdrawing that electron density, helps disperse the charge, negative charge of that conjugate base, making it more stable. So here you will have this carboxylate, and here is the benzoate. We're gonna have this. And now this whole group is electron withdrawing group. When that happens, ARIO says atom is the same in the conjugate base charge on oxygen. Resonance in, say, the carboxylic acid group. This is the same. We can do this in both. But now I have a group that actually is removing electron density at the conjugate base. So that makes this base more stable, weaker base, so stronger acid. And so the pKa's, to illustrate that, pKa of acetic acid is 4.75. pKa of benzoic acid is 4.2, slightly more acidic. And let's do the pKa's of this two. Phenol, pKa is 10. And most alcohols are between around, say, 16. I don't have the exact number, but about that. So clearly, with the pKa's numbers, we know that. So now we have, there are other effects. We can have as electron withdrawing groups. Atoms such as, for example, if I had chloroacetic acid, that will be stronger than acetic acid. But inductive effects are additive. So if I have dichloroacetic acid, that's expected to be even more acidic than that. So I'm going to do this, more acidic. And if I have trichlorine, I'm going to have trichloroacetic acid. And here, so 3 atoms are actually more electronegative than carbon. So I'm going to draw these vectors. So these 3 electron withdrawing groups, or atoms in this case, are going to contribute to disperse the negative charge in the conjugate base. So this is the strongest acid of this series: acetic, chloroacetic, dichloroacetic, trichloroacetic acid. pKa here, I think it is around 0.7 or something like that. So way more acidic than that. So this is, if you round that up to 5, the Ka is 10 to the negative 5. This is, say, rounded up to, you can say the equilibrium constant here is about 10 to the negative 5. So it's not product favor, but this is even better. So 10 to, say, if you round this to 1, well, just 10 to negative 1. So 10 to the 4 times stronger acid. So 10,000 times stronger acid. All right.